Okay, so I'm Joe Warner. I'm a PhD student at the University of Warwick, and I'm here to speak to you about axisymmetric column collapse in a rotating system. So quickly, just want to give you a bit of motivation from where this started. So it originated from the idea of spreading a seed and fertilizers on a field. So for example, on the back of a tractor, you have this hopper and centrifuging disc arrangement. So material is fed in, lands on the centrifuging disc, and material is spread out. So this hopper delivery system has been analysed previously by authors such as Schimbrot and Lillikerker, but I've taken a slight modification of it so I could analyse the flow. So I switched to an initial fixed static mass, moving the initial mass flow, the hop height, and the history of the flow. And this led to the current arrangement. So we have a cylinder positioned centrally on a table of radius r0, which is filled with granular material to a height h0. This is then set into rotation, allowed to enter solid body rotation, and the cylinder is quickly removed and the collapse allowed to happen. And we'll dimensionalize and analyze the pile. So this is an extension of experiments by Lube and Lechanus, among other authors who have done DM simulations as well. So we've got an initial aspect ratio, the height over the initial radius, trialed several different cylinder sizes, a range of aspect ratios as given here, and a frequency range. And the particulate which I used in this case was limestone particulate, mean diameter 600 to 800 microns, with the angular repose and angular internal friction as given there. So this is still similar to a dam break situation, but it might be of interest in the future to looking at granular rheologies in different flow regimes. So I first of all just want to quickly talk about the static case. So here we've got our granular column. It's going to be allowed to collapse with the cylinder removed. So what you'll see is that there's some crumbling at the periphery of the column, which then spreads out radially, and the other layers over the top will then spread over the rest of it. So available to me for the static case, we had a 3D laser scanner, which enabled high accuracy, non-intrusive measurement. So we're talking to the order of up to 10 microns, 50 microns, which is obviously more than enough resolution. So we have the laser scanner on an articulated arm, shown to the left here, which produces a laser stripe, which we then traverse over the deposit, and in real time, this is translated into a point cloud, which we can then turn into a mesh of the resultant pile, as shown here. So discussing what happens in this static case, we have two different regimes dependent on the aspect ratio, also a little bit dependent on the particulate which you're using. So in the first case, when the aspect ratio is less than 0.78, we have crumbling at the periphery, but we're left with this truncated cone shape. But then as we surpass this aspect ratio, we are left with a full conical shape. This figure of 0.78 is related to the angular internal friction, just by definition, because this is going to be the failure envelope over which subsequent layers will avalanche. With this equipment, in the truncated cone case, you get a circular summit, and with this equipment, because of its non-intrusive nature, I was able to get some summital scaling. So in terms of the summit radius, RS, I was able to normalise against the initial radius and found the scaling to be linear when you compare it with the aspect ratio. In terms of the final height, where in the truncated cone case, the final height is the initial height, and then as we pass this aspect ratio, the height actually stagnates, so results in these scalings here. In terms of the final run-out scaling, I found something slightly different to previous authors. So if we take the final run-out of the pile to be RF, and normalise it against the initial radius, so we've got this R star, then in agreement with previous authors, I found this to be linear. So as we increase the aspect ratio, the final run out is going to increase. But what I found slightly different is that this is different for different initial cylinder sizes. So there is a dependence here. This gradient increases as you increase with cylinder size, and so I ended up with this relation here, slightly different to some other authors. So this can be explained, I propose this can be explained by by the jamming and the pressure within a larger aspect ratio, larger initial cylinder size for the same aspect ratio, and something I'm going to investigate later, which I'm going to talk about. In terms of total time for collapse, it's known the normalized final time for collapse is proportional to the square root of the aspect ratio. I was also able to look at the angle at the base and at the summit of the pile. So to the left, we've got this angle at the summit for different aspect ratios, different cylinder sizes. They all fall on roughly the same line, which is an exponential line, and is always less than the angle of internal friction. As for the angle at the base, again, an exponential relationship, but it's different for different initial cylinder sizes again. Also note that it's always less than the angle of repose, as you would expect. So now with this in mind, I'm going to talk about a rotational case. So we're going to see the same sort of start of this collapse. There's going to be crumbling at the periphery of the column, which then the rotation will encourage it to spread further, with some movement in the azimuthal direction, over which the subsequent layers will collapse. But then once this spreading has passed some critical radius, we get some volume loss occurring. So the residual deposit left in the middle, the radius of this will contract until it's hit a stable state. So to explain this diagrammatically exactly what's going on, we've got a side view and a top view going on here. So we initially start with this radius R0 before the cylinder is pulled up, so we're in rotation here. Once pulled up, we have this spreading phase and spreads out to some maximal radius. If we haven't surpassed this critical radius, then this is where we're going to end up, and this will be the final radius of our deposit. But should we have surpassed this critical radius, then there's going to be the contraction, as you saw in the video, and this period of volume loss until eventually settles just roughly at this critical radius itself. And this will be the final radius of the pile. So, throughout this analysis, I'll consider a normalized frequency, as given here. And first of all, discussing the onset of the second regime. So it occurs at a particular aspect ratio, and as we might expect, because there's additional spreading with the introduction of rotation, as the frequency increases, the onset of this will occur at a lower aspect ratio. And since this introduction of rotation tilts the effective angle of gravity, we can assume it's going to decrease by some factor of tan theta, as given here. And some factor, we're taking that the rotation is going to occur at some mean radius, r bar. So plotting this experimental data and comparing the aspect ratio for the onset of the second regime with the frequency squared, we find that it fits quite neatly onto this line in agreement with the relationship of both. In terms of the final run out, so as shown here, we've got what happens when the frequency is 0. So linear relationship dependent on the initial cylinder size as discussed. So what I'm showing here is when the initial cylinder size is 3.6 centimeters. As we increase the frequency, then the gradient of this line increases. And also notice that at some point this stagnates as well. And so there's no further increase in the final radius of the pile, there's just additional mass ejection. So we have it settling at this critical radius, but what I want to know to further understand is how does this gradient vary with frequency? again, consider a normalized gradient P, so the gradient of that line was P, consider it normalized against the initial initial gradient when the frequency was 0, P naught. And so when the centrifugal forces aren't particularly strong, we don't have too much going on here. We have a slight increase in this gradient, but then when it begins to dominate, it falls to this, S squared relation. I hate Windows 8. Falls to this F squared relation. So flipping the analysis around, if we consider fixed aspect ratios but increase the frequency, as we've seen from the videos, as we increase the frequency, the runout is going to increase up to a point, and then we get contraction of this critical radius. And so then the final radius of the pile is also going to decrease, following this line as shown here. And this critical radius can be defined by a relation given there. As a side result, this must be occurring when the frictional forces between the granular material and the table itself are equal. And so by some quick mathematical manipulation, you can actually determine the frictional coefficient between the table and the granular material, as given that. So we can put this all together and we get an absolute mess, but we can calculate everything. So for the final run out of the pile, final pile radius, given some initial parameters and knowing what's going on in the case of no rotation, we can calculate the final run outs. In the red case is where we've just got the spreading phase and we don't have any volume loss. In the green is where we have this spreading phase, which all falls onto a single line. As for the final height, similarly as to the static case, although we've got this occurring faster depending on the frequency, so the initial height is going to be the final height when we're in the truncated cone case, defined by the onset of the second regime, as to when we get this transition, and so this can be given by this relation here. In terms of the time evolution, this became difficult if you're considering the case where you've got volume loss, because it's quite hard to determine exactly when it's finished, because we're going to have particles trickling off towards the end. I only consider the case where we've just got this spreading phase. And it still follows this root A relation, and the increase in the proportionality constant is linear with the frequency. Briefly mention about the volume loss and how this increases. So if you're looking at a fixed frequency, volume loss is occurring. The percentage mass loss increases, accelerates first of all, steady phase, and then a deceleration phase. So just briefly to mention where I'm going to take this research next. So I'm performing some X-ray CT investigations at the moment, just collected all my data. So in terms of the static case, I want to look at what's going on inside the pile post-collapse. So I don't have a temporal stage here. I'm just looking at spatial. So here we've got the picture. We've got to the left, we've got the X-ray head, which is going to fire X-rays. Some will be absorbed by the pile and then collected by the computer. We can see a 3D structure and look all the way through the pile. And so what I'm going to investigate is the porosity of the pile and compare this pre and post collapse. And should show where this failure envelope is going to be, and also we should get some nice gradient scalings of porosity, which will indicate parts of the collapse. Also got some DMM simulations going on as well, which I'll show very, very briefly. This project started a little while ago, got distracted with the experiments. So instead we've got spherical particles, so we're going to have some rolling around, and there's no pile left towards the end. So we've gone for DMM simulations. In the XZ plane, so as you would expect, standard sort of collapse. But what's interesting is what happens in the XY plane. So as I said, we've got this initial phase of spreading. This is the rotational case I'm think I said that. But then we get some spiral arms begin to form, which spread radially outwards. And as far as my analysis has gone, as far as this analysis has gone, all I know is that the particles stay within the spiral arms. They do not jump between different arms. And so I will leave that there. I'll leave you with a summary on the screen and open the floor to any questions. Thanks.
Charlie, come on.
You're always trying to figure out the spiral arms.
Have you investigated how the particle size is affected in the rotational environment?
In the rotational case, no. I haven't got that far because there was quite a lot of experimental data to get, and when you're varying the frequency and the aspect ratio, I think I had something like 300 experiments to get where I got. Although now knowing the scalings, this is obviously easy to investigate to see how far it would affect. But I think as long as it's not spherical, in the case where you've got a normal particle, it'll be more dependent on things like the angle of repose and particularly the angle of internal friction. Yes.
How thick are those spiral arms in the last?
So back, how thick are the spiral arms? The cylinder.
At the height, I should say.
Oh, they are 1B thick, so it ended up as a monolayer at this stage here.
Do the spiral arms expand? Do they diffuse outwards?
Yeah, they diffuse all the way outwards and then eventually disappear.
So they merge into a sort of a homogeneous.
Yeah, so they just expand and completely dissipate. This is something which I did quite a while ago, got lost in the experiments, and now I'm coming back to it. As far as I'm aware, there's not a dependence on the initial aspect ratio, there's not a dependence on the frequency, you still get a spiral arm. So I believe it's between a ratio between the cylinder size and the particle itself, particle diameter.
Restitution coefficient?
Restitution coefficient, I didn't get as far as testing that.
Are they entirely dynamic then?
You
never see it come down to a stable state where they're still there at the end.
No. The curvature increases to an extent that at the periphery they start to collide and then it disappears. In experimental case, I've tried several experiments. You've got, once they're too small, the frequency can often not be large enough, so you still have a part in the middle. But then if you go to the other extreme, so for example 6mm BBs, this is 1mm particles, an experiment 6mm BBs just moves so fast that you don't get any spiral arms at all. So I think it's very sensitive to an initial condition. Probably this ratio of particle diameter to the cylinder size itself.
Further questions? No. Thank you very much.